Okay, welcome to our usual meeting at GEOTOP-A, and we are very happy to have Colin Adams, Williams College, talking on hyperbolicity for knotoids, generalized knotoids, and staked links. To you, Colin.
Thanks. Thank you very much, Renzo, and thanks very much for the invitation to give this talk. I'm going to be talking about hyperbolicity for knotoids, generalized knotoids, and staked links. And to get across the idea, first, let me just tell you that a lot of the first part of this work is done with these students. These are students who are in our summer program at Williams College, but they're from all over the place. And so you'll notice by their name, you'll see their undergraduate institution, which is when I worked with them. And then for many of them, their graduate institution. And as you can see, these are very strong students going to very good schools. And it was wonderful to work with them. So, and I'll show you another group of students that comes later. So here is kind of a map of the talk in terms of the time of the talk and then the level of generality. And you'll see I'll start talking about hyperbolic knots, then I'll specialize to knotoids, then I'll specialize to hyperbolic knotoids, then I'll get more general to generalized knotoids, so we'll get more general. Then we'll go down to staked knots, which are a type of generalized knotoid. Then we'll go down to bongles, and then things will just sort of drift off into wherever. We'll see what happens. Okay, so I'm going to be talking about knots and links, and as you know, knots and links are related. You can say that a given two different projections of a knot are the same knot if and only if they're related by Reidemeister moves. And I'm going to be talking about this work Bill Thurston did in the late 70s, where he said that knots come in three types. And the first type is your torus knot that sits on the surface of a torus without any crossings. Okay, so that's our torus knots. The second type is satellite knots, where you take a knot, like this one over here, you thicken it up, and you stick another knot inside it. So that's what we call a satellite knot. The one that's inside is the satellite, and you discard the old one, and you just look at the one inside. And then the third category is hyperbolic knots. And what Thurston proved was every knot is either a torus knot, a satellite knot, or a hyperbolic knot. Now, what do I mean by a hyperbolic knot? Let's take a look at hyperbolic three space in the upper half space model. So I'm going to take the set of all points in three space with z coordinate greater than 0. So it's everything above the xy plane. I'm going to pick my shortest paths, my so-called geodesics, to be half lines that are perpendicular to the xy plane and semicircles perpendicular to the xy plane. So if I want the shortest path from this point here to this point here, it's going to be along that semicircle to get from one to the other. So this is the upper half space model of hyperbolic three space. Here's a couple of other gadgets that are in here. Ignore the dog. This is an ideal tetrahedron. It's made from, I have three vertices. The xy plane is missing, so those vertices are actually missing. Then I've got three vertical planes and one hemispherical plane on the bottom. And so those faces together make up this so-called ideal tetrahedron. This thing over here, this gadget is called a horoball. It's actually infinite because this point right here is on the missing xy plane, which is infinitely far away. So those will be useful to us in just a little bit. We're going to say that a knot or link is hyperbolic if any of the following conditions hold. They're equivalent, but they're just different ways of thinking about the same thing. We're going to say that the link sitting, normally I'll be working in the three sphere, is hyperbolic if its complement, space minus that link, can be given a complete metric of constant sectional curvature -1. Now I'll just mention hyperbolic three space does have a complete metric of constant sectional curvature -1. So we're just trying to give a metric to the complement of that knot that is equivalent to the metric that you see in hyperbolic space. A second way of thinking about it is that you can build that complement by gluing together ideal hyperbolic tetrahedra along their faces, and you glue those together in order to create that particular manifold. And then a third way to think about it is that there is a map from hyperbolic three space down to the manifold, which is a covering map, such that the complement such that the covering translations are all fixed point free isometries of hyperbolic space. So we'll look at an example to clarify this, these three different ways of thinking about what it means for a manifold to be hyperbolic. So here's an example. I'm looking at the figure 8 knot. I'm taking space, namely the 3-sphere minus the figure 8. So that's this green shaded material that you see right here. And you'll notice I have a covering map. That's the map P that you see right here from hyperbolic 3 space down to the manifold, the complement of the knot. I'm also thinking of this manifold as being constructed from 2 ideal tetrahedra that have been glued together along one vertical face. Then I'm going to glue this back vertical face labeled A to this front face labeled A prime so that the edge numbers match. So I have to do kind of a third twist to get them to match. I'm going to glue this face B on the front to this bottom face B prime, and I'm going to glue this face C prime on the back to this bottom face C, always making sure that those edge labels match. It's not at all obvious that if I glued up these tetrahedra in this way, I would get the complement of this knot. But if that is obvious to you, call me and we can write some papers, because generally that is very hard to see. However, it is the case that these 2 tetrahedra here each have a volume of about 1.01494 in hyperbolic space. And because this is a fundamental domain for the particular manifold, that means the volume of the manifold is about 2.0298 ... And that decimal goes on forever. So this is what I mean by a hyperbolic structure on the knot complement. The covering map would come from gluing on copies of these tetrahedra and tiling all of hyperbolic space by copies of these tetrahedra, and that would generate the covering map down to the manifold. Okay, so that's what I mean by a hyperbolic manifold. It turns out that corresponding to these link complements, you get these horoball packings. What we're doing is looking down on the XY plane, and we have a whole bunch of horoballs that are packed together. Each of these circles is the projection of a horoball sitting on the XY plane, big ones, little ones, etc. And every knot that's hyperbolic ends up getting a diagram that looks something like this. And you can then say interesting things about the hyperbolic structure. Here's another example here of a different one. Okay, so as I mentioned, this particular knot had a volume associated with it, and it turns out there's a very powerful theorem called the Mostow-Prasad rigidity theorem that says every hyperbolic knot has a volume associated with it. So we can look at the beginning table of the knots with some invariants listed here, trefoil knot, figure 8 knot, etc. And in red, I have boxed the hyperbolic volumes. Now, you'll remember that I said that the torus knots are not hyperbolic, and that's why I put a volume of 0 for this one. It just means that it's not hyperbolic because that is a torus knot. The trefoil knot is a torus knot, so it's not hyperbolic. The smallest volume for a hyperbolic knot is the figure 8 knot with this volume that I mentioned before, 2.02988. Here's another torus knot, so 0 volume, but then we have hyperbolic volumes for these going up. Here's another torus knot with a volume of 0. And then I look at the next set of, oops, I guess I don't look at the next set of knots. Okay, there's one other idea that I'm going to need here, which is for a surface in a hyperbolic 3-manifold to be totally geodesic. So again, I'm going to think of a hyperbolic 3-manifold. In this case, it's the 935 complement. That is a hyperbolic knot. I'm assuming I have this covering map down, and I'm going to take a particular surface here, which happens to be a Seifert surface for this pretzel knot that you see shaded here. And if I look at its pre-image up in hyperbolic space, I can isotope it so that its pre-image is made up of a whole lot of copies of perfect geodesic planes in hyperbolic space. And I've drawn one of them here. That's a hyperbolic 2-dimensional space sitting inside hyperbolic 3 space. So it's a very, very pretty surface, kind of, flat in the sense of it being a hyperbolic 2-dimensional geometry inside of hyperbolic 3 space. So that's what I mean when I say that a surface is totally geodesic. I'm going to need that idea in just a second. Okay, so now I'm going to be looking at link complements in more general 3-manifolds, and I'm going to say that a link complement in a 3-manifold is TG hyperbolic. TG will stand for totally geodesic. if after capping off any spherical boundaries, that actually won't come up for us, shaving off any toroidal boundaries, I'll just remove those tori, there's a hyperbolic metric on the complement such that the higher genus boundaries are totally geodesic. So in this example that you see right here, I have a knot living in a thickened surface, a thickened genus 2 surface. And for that to be TG hyperbolic, I need it to be hyperbolic such that that outer boundary, which is that genus 2 surface you see on the outside, is totally geodesic, and that inner boundary, which is that genus 2 surface you see on the inside, is also totally geodesic. And it turns out, just like was true for knot complements, when that occurs, the associated volume is unique. Okay, so that's what we mean by TG hyperbolic. I'm going to use this big theorem due to Thurston, which essentially says that you can turn a question about whether or not a manifold is hyperbolic into a topological question. That's a geometric question. You can turn that into a topological question with a few very simple exceptions. Any compact, orientable 3-manifold with boundary is TG hyperbolic if and only if it contains no properly embedded essential disks, spheres, tori, or annuli. So only these 4 types of surfaces that I have to worry about. And if I can eliminate those 4 types of surfaces, and we can talk later about what I mean by essential, but if I can eliminate those 4 types of surfaces, I can then prove that my particular manifold or link complement in a manifold is hyperbolic. So we'll use that shortly. Okay, so now we're going to move to knotoids. And some of you are probably familiar with knotoids, but some of you may not be. I'm going to say a knotoid will be an equivalence class of emergence of a closed interval into the 2-sphere, or sometimes I'll put it in the plane, but right now we'll think of it as the 2-sphere. So here's an example of one of those immersions. So it's just a projection of an interval into the sphere or plane. And I'm going to allow it, I'm going to allow myself to manipulate that with an equivalence up to Reidemeister moves. So my standard Reidemeister moves. But clearly, if I can just move things around, I would just untangle the thing. So I also need these forbidden moves. And the forbidden moves say that you cannot take a strand that passes over near an endpoint and just slide it off the endpoint. Okay, we're not allowed to do that. So that's going to prevent me from disentangling these things. And this was an idea due to Tureyev that has turned out to be very interesting. And these endpoints of the knotoid, we're going to call those poles. And just remember, we can't pass across them. What are knotoids good for? Well, actually, there are some very interesting applications of knotoids. One of the applications has been in trying to understand proteins. And proteins can get knotted. There is the knot prot, which is the collection of all of the kind of topological properties of known proteins. And so people have been studying that for a while now and trying to understand how can you keep track of whether a given protein is knotted. And one idea is to project it down to the plane and then keep track of what you see as a projection of a knotoid. So in this example here, you start with a protein, you draw it and using sticks to represent the protein with the 2 endpoints, then you project down to the plane and you see a knotoid. And so that's an idea that people have been using. In fact, you can project in different directions. Different directions will give you potentially different knotoids. So you want to try to keep track of all the possibilities. And one of the ways to do that is to project from all directions. And so you can take a fixed knotoid, you can project from all the directions, and you'll get a sphere's worth of possibilities. And different colors on this sphere correspond to different knotoids. So I look at it from this direction, I see this knotoid, 4.2. I look at it from some other direction, and I see this knotoid, 6.12. And then I just keep track over all the sphere of all the different regions that correspond to different knotoids that we see. And all of this appears in the knot-prot database that has now hundreds of thousands of knotoids in it. So this is a good way to keep track of proteins. Okay, so now we want to look at knotoids more carefully, and we're going to use this trick, which is originally due to Gugumsu and Kaufman, but there's a nice paper also by Kodakostas and Lambropolo about this, but it's originally due to Gagumsu and Kaufman. And the idea is we want to prevent the knot from passing across the poles. So how about put some rails on the poles? So these are perpendicular to the projection plane. We put these rails on, and the rails prevent the knot from passing across those poles. So now I can no longer push this particular strand of the knotoid past the pole because the rail prevents me from doing so. So that was the idea, okay? We're going to do a slight variation on that. What we're going to do is we're going to remove neighborhoods of the poles from the ambient space. So I've got my knotoid living in an ambient space. I'm going to remove a neighborhood of each pole. And now the knotoid is incapable of passing across there because there's just no space there. There's no points in there. They've been removed. The interior of these neighborhoods of the rails are gone. So I cannot pass the strand of the knotoid across there, okay? And the theory of knotoids is equivalent to the theory of rail diagrams, is equivalent to this theory of missing rails. And that's the one we're going to be interested in. Okay, so I want to be able to understand what it means for a knotoid to be hyperbolic. And so what I'm going to do is the following trick. I'm going to start with my knotoid that has been projected onto a sphere. I'm going to remove a neighborhood of each of the poles, the interior of a neighborhood of each pole. I'm going to take that diagram and I'm going to reflect it across a plane to get a second reflected copy that you see labeled S upper R. So I've got my original copy here and my reflected copy here. Now what I'm going to do is glue the little boundary of that neighborhood of my pole here to the reflected copy of that boundary of the neighborhood here. So I'm going to do it for my first pole here and for my second pole here. And that will take my two punctured spheres and put them together to create a torus. So I started with a sphere with two poles. I glue them together along the missing neighborhoods of the poles, and I end up getting a knot. You know, and I used to have a knotoid up here, a knotoid diagram here and a knotoid diagram here, but I glue the endpoints together and now I get a knot living in a torus, okay? And I can think of that knot diagram living on a torus as a knot living in a thickened torus. So I go from my original knotoid to a knot living in a thickened torus, okay? We're gonna see that a second way right now. So this was the first visualization. I could have done that by starting with my knotoid living in a thickened sphere, again, removing a neighborhood of each of the poles. Then I could open up those neighborhoods of the pole. You'll notice here I have an annulus boundary and another annulus boundary, and I could widen those out so that I have my annulus boundary on the outside here and my annulus boundary on the outside here. And then I take a reflected copy, I guess this was the original, and I take a reflected copy, and then I glue those annular boundaries together here and here, and here and here, and again, I get my knot living in a thickened torus. So I can think of it either in terms of the diagrams, or I can think of it in terms of the thickened spheres. But either way I want to think about it. In either case, I start with a knotoid, and I end up with a knot living in a thickened torus. And then using that knot living in a thickened torus, I can then determine whether or not it's hyperbolic. And if it's hyperbolic, I can get a hyperbolic volume for the knot living in the thickened torus. And then I take half that volume, and that's the volume of my knotoid. So now we're going to look at some knotoids in the volumes, and you'll notice that, in fact, other than this one right here, which is not hyperbolic, all the rest are hyperbolic, and they have volumes. And it turns out if you go through the 104 knotoids of 4 crossings or fewer, maybe it's 115 of those, all of them except for this one are hyperbolic. So it turns out that hyperbolicity seems to be a really powerful invariant for distinguishing between knotoids. Okay, so that's knotoids. Now I want to try talking about generalized knotoids, and this was work that, again, that stuff I already talked about was that small group. That's the summer group from 2022. This is also, as we were working through knotoids, we started thinking, why do we need the poles to only have one strand coming in? And so we started thinking about generalized knotoids. So this is going to be the idea of a generalized knotoid, and you'll notice that my poles can have one strand coming in, two strands coming in, three strands coming in, as many strands as you want coming in. They can even have no strands coming in. Okay, so these are going to be my generalized knotoids. I'm going to allow, I'm going to have, so it's going to be an immersion of a graph into either the two-sphere or the plane with crossings delineated, considered up to isotopy, Reiter-Meister moves, but I'm also, again, going to have forbidden moves. And my forbidden moves, the first one resembles the forbidden move I had for knotoids, namely, if I have a pole, I cannot take a strand and slide it past the pole. So poles block me from passing strands across them, just as they did for knotoids. There is one other move that comes up here, however, and that is what we don't allow is if you have a bunch of strands coming into a particular pole, you cannot take two of them and just twist them around each other. In other words, you can't, I don't know if I can do this with my fingers, but you can't twist them around and tangle them up that way. That is not allowed. Sorry, it went forward and I didn't want to. Whoops. Yeah, okay. So those are the moves that aren't allowed. And it turns out that this idea of generalized knotoids actually encompasses a lot of ideas that have existed before, okay? So we have this idea, we've got a surface, I said it could be the sphere or the plane, but can be some other surface, and an equivalence class of diagrams up to local Reiter-Meister moves and isotopy not allowing forbidden moves. A spherical knotoid is definitely a generalized knotoid. A plane... Sorry. Are we getting a question or is that just someone's mic on? I can't tell. I couldn't understand that if it was a question.
No, I think it was a mic on, so
okay.
That's all.
Okay, thanks, Renzo. Yeah, so spherical knotoid is an example of a generalized knotoid. A planar knotoid is actually a generalized knotoid. It's just a regular knotoid with one extra pole, which you can think of as sort of a pole at infinity that prevents you from pulling things around the outside of the sphere, and that makes it a plane. So you can think of it that way. Whoops. A classical knotorlink is a generalized knotoid with no poles. Multilinkoids, which are just knotoids with multiple components, those are definitely generalized knotoids. You can also have what are called polar knots that people have defined before, where you have poles on the knot. You can also have long knots, which look like this, which you can think of as a polar knotoid, as a polar knot with one pole at infinity. So all of those fall into the category of these generalized knotoids. You can have so-called string links. We won't take the time to look at this, but string links are really links that live in a solid cylinder like this, and you can think of those as knotoids with one pole. And then this is the one we're going to spend some time on. We'll come back to this in a second. And these are staked links, which are link diagrams where we simply add poles that are valency zero. They don't have any strands coming into them. And those turn out to be a very interesting category. So we'll come back to those in a second. But first we have to define what it means for a generalized knotoid to be hyperbolic. And this is the way we're going to do it. So we take our generalized knotoid, we realize it in a thickened surface. We do the same trick we did before, which is to remove neighborhoods, open neighborhoods of all of the poles in this thickened object. So we get an object that looks like this. And then I'm going to use that trick that I used in the case of a regular knotoid, where I'm going to take this annulus that you see right here, and this annulus here, which are the boundaries of the neighborhoods of the missing poles, and we're going to slide those up to the top. So we're just going to pull them up to the top. So you see them appearing right here. You'll notice I do it only to the ones that have endpoints on them. Okay, so endpoints of the generalized knotoid on them. I do not do it to the one that does not have an endpoint on it. So I pull those up to the top. I take my object, I take a reflected copy of it, I glue the annuli together that I've pulled to the top, and I get this new object, which you'll notice is a knot or link living in a handle body. And then I say, if that thing is TG hyperbolic, then the generalized knotoid is hyperbolic, and its volume is exactly half the volume of that object. Okay, so now we have a well-defined notion of what it means to be hyperbolic for a generalized knotoid. Okay, I'm going to take a break here and ask for questions because I realize I'm throwing a lot of stuff at you. So are there any questions that anybody has at this point? Everybody's good?
Dewitt, put your mic on.
Sorry. Okay.
Okay.
Now the mic's on. Okay.
Yeah.
So how do you classify these things? I mean, you get these by doubling up, you get knots and links in these handle bodies, but do you then compute polynomial invariance, or is it
No.
hyperbolicity just
Yeah,
the only tool you've got?
Yeah, so you definitely can, and actually in our paper that we wrote about this with the students on generalized knotoids, we did generalize a lot of different kinds of polynomials for them. So there are polynomial invariants for these objects, for these generalized knotoids. But for the purposes today, I'm just talking about the hyperbolic invariant. And so the hyperbolic invariant, which is a really powerful invariant, will allow you to distinguish lots and lots of these generalized knotoids by doing that operation, the doubling, and then finding the volume of that object. That's going to give you a unique invariant that you can associate to that particular generalized knotoid, and then you can use that to distinguish between them. But the polynomials are also very effective at distinguishing between these things. Ken?
Yes, Ken. Go ahead.
Back to your discussion of knotoids.
Yeah.
In your calculation of hyperbolic volumes,
Yes.
do you have the uniqueness result for the knotoids as you did for the knots?
So yes, in the sense that the Mostow-Prasad rigidity theorem does apply. And so given a knotoid, it will have a unique volume associated with it. It does not mean that two different knotoids must have different volume. And that's also true for knots, that you can't distinguish all knots with volume. There are knots that have the same volume, but the vast majority of knots have distinct volumes, and the vast majority of knotoids have distinct volumes.
Great, thanks.
Yeah, and I'll mention one other thing about the knotoids that I didn't say, but it's my favorite thing about the volumes of knotoids, which is if you compose two knotoids, so you just glue the end of one to the beginning of another, and they're both hyperbolic, the volumes add. If they're both hyperbolic, the volumes add. The new one will be hyperbolic, and the volumes just add. And that does not happen for knots, but for knotoids it does. So that's a really nice feature. So, it helps you if you're looking for factors, knotoid factors. It makes life a lot easier. Any other questions?
If I may, I just have a very basic kind of historical note. I forgot, the origin that brought people to consider hyperbolic volume, and also the fact that even the first information was already on digits that are several digits, decimal digits. I wondered, can you remind us how was determined the first few numbers, say?
Yes, so
they were done by hand, I imagine.
Yes, so originally the first person who kind of realized there were hyperbolic knots that had hyperbolic complements was Robert Riley. And Robert Riley was a graduate student at Southampton at the time, and he was an older student. And Bill Thurston happened to visit Southampton at that time, and Bill Thurston had been thinking about such things. And seeing what Robert Riley had produced, he then realized that, in fact, many knots were hyperbolic. And then, of course, he went way beyond that and came up with the geometrization conjecture and did all kinds of things. But all of the hyperbolic knot stuff started with Bill Thurston. And then people started calculating volumes. And so the figure 8 knot was the first one, and it was calculated out of ways. And then when I was a graduate student, my professor said, I will give $5 to the first person who finds the volume of the 5-2 knot, which is the next hyperbolic knot in the table. And I was a starving grad student, so I thought, okay, I'm gonna solve this problem. And I spent a month working on it. After a month, I started to think maybe
$5
wasn't enough.
Okay.
And then somebody else solved it. A postdoc named Dennis Stowe solved it. And I was brokenhearted, and my method didn't work and his method worked. But when he presented it, I realized what I'd been doing wrong, and I fixed my method. And his method only worked on the one knot, and my method worked on all the rest of the hyperbolic knots in the table. So he got the $5, but I got a PhD. So I was very happy about that.
Okay, thank you. I
Yeah,
now realize how a PhD is worth.
yeah, yeah. I was very happy with the end result. And that's how I got into hyperbolic stuff. That was really what started it. And then I also got interested in other aspects of knot theory as well. Okay. All right. Shall we continue? So back to staked knots and lengths. So you'll remember what we said is we're going to take a diagram. We're going to stick some of these poles in it. And we are allowed Reidemeister moves, but we're not allowed this forbidden move. Okay. So we're not allowed to push a strand across a pole. And after we came up with this idea, it turned out, I mentioned it to Luke Hoffman, and he mentioned that he actually had come up with this idea, I don't know what, 30 years earlier in a paper called Knots, Tangles, and Electrical Networks with Jay Goldman. And they had come up with this idea of sticking in these so-called tunnels that prevented a knot or link from going across. And it turned out to be relevant to the stuff they were doing on electrical networks. So, you know, and I felt like a little, too bad. But on the other hand, you look at it on the bright side, I'm only about 30 years behind Luke Hoffman. That's pretty good. All right. So I want to think more about these staked knots. And I'm going to picture them right now. I'm thinking of starting with a projection on the sphere. I'm going to thicken the sphere. So now I have a thickened sphere there with these rails in it. I'm going to remove neighborhoods of the rails. And I now have a picture that looks like this on the left. Now what I'm going to do is I'm going to take that bottom hole that I put in there, so that bottom tube, which is open, and I'm going to widen it out. So I'm going to widen it out and pull it around until I get to the picture on the right. And then I realized that that picture on the left actually represents a knot living in a handle body. Okay, so I've turned my original staked link or knot into a link or knot living in a handle body. And then I can say it's hyperbolic if and only if the complement of that knot in that handle body is TG hyperbolic, keeping in mind that means the boundary has to be totally geodesic. Okay, so now I'm interested in links living in handle bodies. And so if I put in one stake, just going back to that previous picture for a second, if I just put in one stake here, I would have a sphere boundary here, a sphere on the outside, and then a tube between them. That would be a spherical boundary. And in fact, then I would just be in a ball. And so one stake just makes a knot in a ball. And you can cap off that ball with another ball, and I just have a knot living in the three sphere. So that's not new. That's not different. So I'm not really interested in that case. Two stakes, if I put in two stakes, well, topologically, that's the equivalent of removing a neighborhood of this trivial component that you see right here. And so that's just a link with two components, and we've been thinking about those for many years. So that's not particularly interesting to me either. So what I'm really interested in is a hyperbolicity of 3 or more staked links. Now, if I have 3 or more stakes, then I get a knot, then I get a knot living in a handle body. And so we'd like to know whether or not it's hyperbolic. And so the first thing that we did once we realized this is we went back to the literature and we searched for examples of hyperbolic knots living in handle bodies. We wanted to find who had thought about this before. And I got to tell you, I was a little surprised to find out that it was me. So it turned out that Alan Reed and I had written a paper in 1993, so that was 30 years earlier, where we came up with one example of a knot living in a handle body, and that was this one that you see right here. So that's the first example I have been able to find in the literature of a hyperbolic knot living in a handle body. Then 10 years later, Frigerio extended it to an infinite class of examples where he took the complement of this graph and this knot. That turns out to be a generalization of this one example we had here. So now he has an infinite number of examples, and he proved all of those were hyperbolic and actually found volumes for them in very explicit hyperbolic examples. Frigerio, Martelli, and Petronio in 2004 found this example, which currently is still the smallest volume example known. Not that it's been proved yet, but it's the smallest example known. But it wasn't until 2018 when Howie and Purcell did a very general version of alternating projections that they found lots and lots of examples of knots living in handle bodies satisfying certain conditions that proved they were hyperbolic. So now we have lots and lots of examples coming from that. But I'm going to tell you about another way to get these, and this is joint work with one of those students I showed you before, Joy Chen. And what we're going to do is we're going to think of a disc with some holes in it, and then we're going to thicken it up. That's going to be a handle body again. But this time, unlike what Josh Howie and Jessica Purcell were doing, we're going to project to the intermediate surface in this product. And we're going to look at an alternating projection in that intermediate surface. Okay, so this is the theorem. The first part just says we have a closed orientable surface and a link in the thickened surface, just as we saw before. We're going to insist that the projection pi of L is alternating. It's cellular, which means that each of the complementary regions is a disk, and then we're going to add in the stakes. And so the stakes are going to be represented by points, so it's a finite collection of stakes. And there's a couple rules about how we have to choose those stakes. First off, the diagram has to be weakly prime. That just means, notice here, this does not look like a prime knot right here because it has a disk with interesting things going on the inside of the disk. And so we're not allowed to do that. But if we want to fix something like that, we can just add in a stake in the middle of this diagram, and that makes it prime again, okay? So if we have any regions like this, we better stake them in order to prevent them from wrecking our ability to make this totally TG hyperbolic. Number two, in any region in the link diagram, you can only put in one stake. You can't put in more than one stake. Number three, no two adjacent regions both get stakes, okay? So these are all really easy to check. Somebody gives you a diagram on a surface, very easy to boom, 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 put in your stakes and satisfy these conditions. The fourth condition is the weird one, and I'm not even going to tell you what it is. I'll show you pictures of it in a second. You can't have any pond path curves, and I'll explain what a pond path curve is in just a second. Then the resulting stake length will be TG hyperbolic. That's the idea, okay? So if we satisfy these conditions, start with an alternating diagram, stick in stakes appropriately, we will get something that's TG hyperbolic. All right, so let's look at some examples and explain what a pond path curve is. Okay, so here's my first example. I've already removed neighborhoods of my stakes. And this diagram here, my staked regions are not adjacent. They're not in the same region. And I'll explain pond path curves in a second. That's fine as far as pond path curve goes. I could also do it on a torus. Here I have 3 stakes on a torus. And again, the staked regions are not adjacent. They're not sharing a region, and there aren't any pond path curves. What is a pond path curve? In example C, we have a pond path curve in red. I want you to imagine a beautiful park, and you're walking along a closed curve in the park, a path in the park, and as you come to an intersection, you cross another path, and if you went right, you'd go to a pond, and if you went left, you'd go to a pond. And then you continue along your path and you come to another intersection, and again, you can take a left and hit a pond, or you can take a right and hit a pond. And that's what we mean by a pond path curve. It's just a beautiful path in a park with lots of ponds to either side. So here is a pond path curve. Here is another example of a pond path curve. Every time we come to an intersection, we can go left to a pond or right to a pond. And therefore, that's a pond path curve. And the existence of that prevents TG hyperbolicity. Okay? So that's the theorem. I'm not going to go through the proof of that theorem. That would take a long time. But we will use that to our advantage. Okay. What's bad about pond path curves? I'm not going to go through this explanation here, but in blue there is a pond path curve, and it turns out that we can build an annulus. And you remember that theorem by Thurston that says no essential annuli. We can build an essential annulus. In purple here you see one disk of the 4 disks that we would use to actually generate an annulus here. That's one of them. There's another disk behind here, another disk in the front here, and those 4 disks fit together to create an essential annulus, which precludes TG hyperbolicity. But But you can see that, in fact, these pond path curves cause a problem. Okay, so now let's get back to what we were interested in, hyperbolicity of staked knots and links. And I claim that every knot or link in the three-sphere has a diagram that can be staked to be TG hyperbolic. And I'm going to do this a little bit quick because I have some other things I want to talk about. The idea is the following. Take a diagram of your knot or link. It's probably not alternating. I'd like to use the theorem of Joy Chen and me to get hyperbolicity. So I'd like to be able to stake it, to turn it into to be alternating. And I'm going to note the following fact. If I'm in a thickened surface like this, and I stake on either side of a crossing, so here I've staked on either side of the crossing, and here you see the 3D version of that, you'll notice there's this disc now that has boundary and the boundary of the handle body that is punctured twice by the knot. And if I cut along that disc, twist one side 360 degrees, and then glue back together, I will be gluing the same points that I glued before. So that will be a homeomorphism of the complement, but it will reverse the crossing from being, one way to the opposite. Okay. So in other words, once I put stakes in on either side of a crossing, I can do this operation and I can switch that crossing to the opposite. And in particular, if I do this at each crossing, I can change every crossing if I can put a stake on either side of it, and then I can change that crossing and thereby make the diagram alternating. Here's one way you could do that. You could just use a checkerboard shading of your diagram. You have a checkerboard shading of your diagram, and then you could stake each of the regions in the shaded surface, and then every crossing could be changed because every crossing would be adjacent to two stakes, and I could change every crossing and make it alternating. So that sounds like a great idea until you realize that that's always going to create a pond path curve. So here in this diagram, you see the corresponding pond path curve. As I travel along the curve, I've got a pond to either side at every crossing, and therefore that doesn't work. So that idea didn't quite work, but I like the basic thesis of the idea, so I want to try to use that. So what I'm going to do is if I have a crossing that I want to change to make things alternating, I'm going to do a little swirl move on it. The rest of the diagram, assuming it's all alternating, will still be alternating, and now my problematic crossing has been moved to here. I'm still not going to stake yet because one of my staked regions would be to the outside and it might come in contact with another staked region. So I'm going to swirl a second time. Now all of this diagram is alternating except for this one problematic crossing. I stake around it, and now I can just, by staking there, I can change that crossing and make it alternating. I do that for any other crossings I have to change, and the rest of the diagram will satisfy all the conditions of the theorem of Joy Chen and me, and therefore the resulting stake knot is now TG hyperbolic. Okay, so that proves that any knot can be staked to be hyperbolic. Okay, I mentioned this before, I won't go into that. Now I want to talk a little bit about this idea of bongles. This is my group from last summer, another great group, and we wanted to look at very simple examples of staked knots, and it turns out you can take the trivial knot and you can stake it by just putting in monogons and staking it, and we can have regions that go out and regions that go in. They can be alternating or they can be non-alternating, as this one goes over, over, under, under, under. And we were trying to understand what's going on. So this is a much simpler example of generalized knotoids, but this is particular stake knots that are generalized knotoids that are very, very simple. It turns out that very first one that I mentioned that Alan Reed and I did is an example of this. So that is the staked that is the bongle that you see right here. The ones that Frigerio was looking at are these ones right here. And I'm not going to go through this because I'm running out of time, but I'm not going to go through this particular theorem, the proof of this theorem, but it turns out we proved that a bongle is alternating if and only if it is hyperbolic. So the hyperbolic bongles are exactly the alternating ones. I'll just show you a few pictures of that. This first part is easy. If it's alternating, it satisfies all the conditions of that theorem. It's weakly prime. Every region contains at most one stake, as you can see. No two adjacent regions contain two stakes, and there are no pond path curves. There are no curves In fact, there's no opposite regions that are staked. So therefore, it's hyperbolic. To show the other direction, what you do if it's non-alternating, I want to show that it's not TG hyperbolic. And the trick is to find annuli in there. And I won't go through this in detail, but you can find annuli in the examples. Looks like this. This is one of the annuli that exists there when it's not alternating. And similarly for other cases, I'm not going to go through that because I want to talk about one or two more things in the remaining minutes. Okay, so what about volumes of bongles? Now I know exactly which bongles are hyperbolic. They're the alternating ones. What can I say about volumes? And I can have my monogons being to the inside or to the outside. So I can shift them from the inside to the outside. And when I do so, that does change the volume of the resulting bongle. So you'll notice the volumes here are different. But interestingly, one of the things we noticed was if you have certain bongles, even if you change the order of the innies and outies, even though they have the same number of innies and outies, but you change the order, the volume stayed the same. So here's a couple of examples like that. And so we define this idea of a bongle with the same number of innies as outies. In this case, I've got 4 outies and 4 innies. These are all 8 bongles, but they have their innies and outies in different order, and they all have the same volume. And we're going to call those balanced bongles. And the theorem we proved was 2 alternating balanced N bongles have the same volume regardless of the order of innies and outies. So the order of the innies and outies doesn't matter. The volume will be preserved. And I'll just quick give you the idea of that. There's this really beautiful result of Dillon Thurston that allows you to decompose a knot complement in the 3-sphere into octahedra. And so at each crossing, you put in an octahedron, and then you glue the faces of neighboring octahedra corresponding to neighboring crossings together in an appropriate way, and you get a decomposition of the knot complement into octahedra. And they have some finite vertices and some ideal vertices. In our case, because we have these monogons, these 2 parts are pulled together, which means some of these edges that you see on the octahedron are actually the same. They get glued together. And then what I'm going to do, because I want to drill out my stake, my neighborhood of the stake, I'm going to drill that out. And when I do that, that collapses this edge labeled 8 on the octahedron down. And now I get a little 3 bipyramid at each of the crossings. And then what I do in the case I have a balanced N bongle, I can actually see that I can use all the same 3 bipyramids at every one of the crossings. I can use the same 3 bipyramids and all the angles on the edges are the same, and every 3 bipyramid is isometric to every other one. And therefore, it's independent of the order of the innies and outies on the 3 bipyramid. Okay, so the volume doesn't depend on the order of the innies and outies, and so all of them will have the same volume. And so then you can start looking at the volumes of various bongles. So here you see the 2, 3 bongles, which have different volumes, and then there are these 4 bongles, 5 bongles, and 6 bongles. Not showing all the possibilities because this one is a balanced bongle, and so I know I could change the order on these and I would get the same volume. One of the things that you notice is the following conjecture, and that is assuming that the number of innies is fewer than the number of outies. As you increase the number of innies toward the halfway mark, the volume goes up. And we have not been able to prove that yet, and so that's still an open question. And I think maybe I will stop there. So I would love to open it up to any questions anybody has, but I really appreciate everyone listening. Thank you very much for being here.
Okay, thank you very much, Colin. Very interesting. Questions, please. I have a very, very, very naive interest, let's say. I remember the work of Philip Boylan more or less 25 years ago, 2000, where he came up with the idea of rods mixing fluid in a tank. So, and of course, the search for the possibly best, according to different definitions anyway, protocol to have an efficient mixing according to the topology of the created topology induced by the motion of 3 or more rods in a say in a tank. I wonder if you can think of dynamics put on points here on stakes and see if there is any possibility to interpret different number of stakes in terms of different number of rods with some dynamics, either preserving topology or breaking topology. Have you thought of that?
No, I haven't. I haven't thought about that at all, and that's an interesting idea. I mean,
Of course, I'm interpreting these diagrams as we see them in a very, very naive way, as if they were just planar, almost planar diagrams with maybe field lines, what we see, or something else. But anyway, this is the idea.
Yeah, no, I mean, it's certainly related, and you could imagine, for instance, take a container, let's make it a cylinder. So take a cylinder, put in some rods built into the cylinder, and then, within it, you put your knot, and then you start spinning your cylinder, and you look at how the knot behaves when it's restricted, when it can't pass through those rods.
Yeah.
And that's really what's
Yeah.
going on, exactly what's going on with these stake knots and links. I mean, they're just, they can't pass through those things, but they can get tangled up just like regular knots do. They can, you can ask all the questions that you ask about regular knots. They're just restricted in these, their motion is restricted in these ways. And
I have a second question that is slightly more abstract, not that much, but
can I just
can
say
we
one thing
interpret
first,
this?
Renzo? Let me just say one other
Yes.
thing. The other place
Sure.
that you see stuff like this, incidentally, is when you think about tying up a boat. You're tying a boat. Well, you
Oh,
don't
sure.
tie a knot, you tie it to something, right? And so in some sense, that's another place where you see a lot of examples like this.
Sure,
Sorry, go ahead.
sure.
I interrupted you. Sorry.
No, it's just interesting. And then I was wondering if there is any other interpretation of these rods in terms of, I'm thinking of intersection theory and indices of linking number, if you like, when these rods are either, again, moving or fixed, and but interpreting these points, these stakes, as indeed as intersection in a dynamical system, something like that.
Yeah, I don't know. I have not thought about that at all. That's an interesting idea. I like that idea too.
Okay, thank you. Yes,
That's
I
an
think-
interesting idea. Yeah, no, I mean, the idea here is, I keep talking about fixed rods, but in some sense they're not, right? Those points can move. If it's topologically convenient to have those points move around the plane, you're allowed to do that. Just
Exactly.
as long as you don't allow the, you
Sure.
don't allow the knot strand to pass across them. So you could imagine, you think about, in quantum computing where you've got a bunch of particles and they're moving around. These could be the particles. They're moving around in various ways, but the knot has to avoid ever crossing the particle. So, you
Sure.
can imagine various
Yeah.
situations where this might be useful.
Yes, I can see hand on Talia. Hello.
Hello.
Hi.
Hello,
Go
thank
ahead,
you.
Talia.
Yeah.
My question is, has the Color-Jones polynomial defined for knotoid? And if yes, if you have checked the volume conjecture works for some knotoids?
So the answer is yes, that people have extended, various polynomials, including the Jones polynomial to knotoids. But nobody has looked at, and it's a great idea, nobody has looked at whether there's a good version of the volume conjecture in the case of knotoids. So that would be something that would be interesting to look at. You'd have to think a little bit about, I mean, you could think of it in terms of, when you take that knotoid and you construct this knot living in a thickened torus, and then you could just calculate polynomials related to that thickened torus, and then you would expect that the volume conjecture would make sense in that context. So you sort of take yourself out of the knotoid category by simply converting it to a knot living in a thickened torus. But it's a good question, and I don't think anybody's thought about it.
Thank you.
Yeah, thank you. That's a great question.
Other questions, please. Okay, if not, all of us thank Colin very much for a beautiful talk. Thank you very much, Colin. Great
Well,
to have you.
thank you very much. This was really fun, and thanks for listening, and thanks for the great questions. And it's good
Thank
to see
you.
everybody. Wonderful to see everybody.